Hello, good evening, everyone. Today we're back to our BattleBot project, which I started last week. What was it? Monday, yeah. Well, today I decided, since we are going to do a little bit of, to start. Let's just say go top down from what we're working on. So we're gonna work first on the rotating sonar, which I was idealizing it. Honestly, I will be honest, I was actually wanting to make a radar, but yeah, unfortunately for that, it would either be too unreliable or too expensive, not to say maybe illegal even, because electromagnetic radiation has some weird laws. So yeah, we're gonna have to go with sonar for this one. And I mean, first things first, a few considerations for design. Yeah, as the as it says in the description, we could any old sonar does work perfectly, but in the type of fixture that we want, it wouldn't be very effective. Or nor practical, since we're gonna be making this one rotating, well, almost a swivel structure. So we gotta sort of work around this problem. And so I kind of on my off time, I came up with two ideas of two ideas to test out for proof of concept, which would be either maybe actually first let me talk a bit, walk through a bit about how I'm thinking of designing this. So basically, it would be, let's just say this is a battle bot, really shitty, a battle box, if you will say. Here is the battle box. So the current plan is to have the radar sort of popping out here on the fuselage and basically scanning all sides. Sort of. This isn't really anything final, especially since we're still in the preliminary design phase. But for this, we would have two ways of really achieving this. The first way would be to just as in any way, we're gonna have to have the transmitter and receiver in a little bit of an offset to account for this one sending. And this is going to be continuously rotating, so when the signal goes and comes back, this won't be here anymore. This won't be at the same location. And yeah, we got to account for that. For the sonar, I found actually, for the sonar module, I found, hold on, let me open it up real quick. It was on Farnell. Don't know if you're acquainted with this site, but it's another electronic supplier. And unfortunately there wasn't anything on RS, but where is it? I'm loading it up over here real quick. Sensori di prossimità. Because I mean, we gotta be honest. We're gonna have to work with this, so might as well find all the parts beforehand. No, this is the sanding. Ah, shit. Yeah, no, this is, we really got on some really expensive stuff. Am I on the right place actually? Might be on ultrasound. Oh no, hold on. Yeah, nah. Need to go directly on ultrasound. Right, so the module I found, I wanted to make this a bit longer range, but the farthest I could find was 18 meters. So let's just say that yeah, we want to focus this on around the halfway point, so we can get a good reception forward and back. This would mean that it would have to travel 9 meters, which isn't really a lot, and then it would have to travel back 9 meters. Yeah, so total round trip equal is 18 meters. Oh yeah. And so the time spent to, well, travel those 18 meters effectively will be around 50 milliseconds, which shouldn't be too bad. With radar you could get this down to the nanoseconds, but unfortunately, yeah, it isn't too bad, but it already gives it already puts into consideration what we gotta do here. So basically, if I'm gonna, for example, make this rotate maybe once per second might be excessive, maybe not. But yeah, let's say if we want to make it rotate once per second, we will want to make these spaced out in a way that they, in the arc, well, we want to make these spaced out in a way that it hits after exactly 50 milliseconds. So yeah, that is a consideration. Then there was the thing, which was actually, yeah, I kept going back and back to it, about either using a sweeping type radar, which just basically always transmits, and then when it receives it receives, or just a pinging radar, which it transmits and it transmits the signal and then waits for a response before transmitting again. I will try both. I will try both the sweeping or pinging radar, and yeah. But, well, for the sweeping radar, we might actually want to get a full range in. We might actually want to get the full range instead of 9 meters. We got the whole 18 meters, which would just basically make this around 100 milliseconds. Always good to write everything down, because since you know, and the general idea would be that basically it's just a circle. Well, you would have this circle. Apologize for my drawing. I'm not the best at drawing circles, but we'll get this. I'm not gonna use this for actual fabrication. This is gonna go. I'm gonna make a CAD model later. So it basically will be a circle. Over here we would have a spindle with a slip ring, because if it's gonna be rotating, we can't really let the cables just, you know, contortion them among themselves. Then we're gonna have a sort of motherboard and two daughter boards here, one with each sensor. Basically, this is the basic gist of the design. Then we gotta calculate how much angle we're gonna need. And well, a bunch of other constraints. Of which I would like to introduce the first constraint. Yeah, I actually didn't want to. I actually didn't think I would. I'm actually not sure if I'm gonna need it, but if I do, I want to minimize cost, let's say. So this is gonna be on a rotating position. This is gonna be constantly rotating. I don't know, 60 RPM or something like that. But the problem is I don't really want friction to. I don't really want to risk friction destroying the plastics, or maybe even you know, fusing the plastic together from spinning too much. So we're gonna have to get a bearing in there. And so to minimize cost, we're gonna have to sort of, well, you know, get something that's affordable and of the size we want. So yeah, let me go back to this. So we're gonna have to get a bearing. That's no surprise. But I want the internal diameter. I did a preliminary CAD model already. I want the internal diameter to be between 60 and 80 millimeters. I realize saying mils kind of makes it confusing for any Americans, so yeah, I'll just say millimeters. Wow. Really doesn't want to work today, huh? Yeah, alright, from... Jesus. Why is it so laggy? Just because we're working. Yeah, let's just go 50 millimeters to... Or you know what? I think I remember which one it was. I'll just find it manually. It was a 65 millimeter inner diameter, if I recall correctly. No? Or was it 60? Might have been 60. Hold on a second. Yeah, here we go. 60 millimeter, 85. Do I have a... do I have a CAD model for this? Yeah, how I'll find the... Oh yeah, I can get a CAD model from SKF. That's good. But yeah, so we're gonna pretty much design our thing around this. Mostly due to, well, not wanting to spend a fortune on a bearing, because this is already expensive as it is. And it's not gonna be really getting that much stress, so yeah, I'd like to avoid having to... Sounds good. The washer... Oh, I'm not gonna... Yeah, I'm not gonna include the washer. I'll make my own out of plastic. I think that at least that we can make out of plastic. I will get it on STL. Right, and I guess with that we can start calculating some other things. Like, for example, we are looking at around 80 to 90 centimeters in... This was... diameter, right? Yeah, it's 60 centimeters, 60 millimeters in diameter. So we are looking at around we're looking at something around 80 to 90 millimeters maximum. So, I mean, if we want to be strictly the size of the bearing, it's going to be 85, but we really want to give some room. So yeah, let's just say 86 or 87 or something like that. Not or 90 just to make it around, so 0.9 meters. So if we wanted to make 0.9 meter, so if we want to make so if we want to find the angle for right, 0.9 meters, which gives us this, assuming an angular velocity of 60 rpm, which, well, it's 1 rps. Yeah, that's pretty much a given. So yeah, if we're assuming we're doing this 1 rps, which again might be a little bit excessive actually, we might want to maybe decrease it later, which is why this is just a preliminary design. So yeah, 1 rps for with 90 centimeter radius would give me well, not the radius, but 45 centimeter radius. So V equals omega r. The linear velocity we're gonna have at the end of this, which, well, this is just for reference, since at the end of the day we're not gonna be mounting it right at the edge. Again, it's not gonna be mounted right at the edge, so we can get that well, omega, this is 2 pi radians per second, so we get a linear velocity of 2.9 meter. I mean, I guess it's closer to 2.8 meters per second. And so this is going to move in the 100 milliseconds is going to move well, 1/10 of this, so 0.28 meters, which should be which should be, yeah, lots of math here today. Should be around what is this, 0.31 radians, or however many degrees that is. Yeah, will be a bit quicker to just do conversion. Yeah, it will be around 17 degrees. So we're gonna have the spacing of around 17 degrees. This, of course, keeping in mind that we keeping in mind that we will have to shrink this a little bit later, but then it's already a start, so we can go for the CAD model. And yeah, on regarding to the system, we'll probably discuss it at a later date. So well, I guess let's stop with this boring stuff and go get some CAD done. Design Spark should be installed, shouldn't it? Yeah. Alright, so let's get this. Oh, I need to sign in. Yeah, hold on a second. No, this might not be right. Log in. Oh, it is. All right. So we can get right on to CAD then. Yeah, I don't need the getting started window. There we go. Whoops. Why is it all buggy? I remember it being this buggy last time Now let's make a new design then. Oh, alright, it fixed itself. Well, first thing first, we're gonna have to import a file. Where is it? Why are you opening up stuff that I don't want? Oh well, whatever. Oh, right. Hold on, I forgot to... Right, it should be over. Huh. How do I import an STL mod? Okay, hold on. File, new design. Right, here we are. Right, so... Oh yeah, because I need to change the type of file. Silly me. STL. Open. Oh, my name is selected. Alright, here we are. This is supposedly the roller bearing that we're going to be using. Which axis is it? Hold on. No, center. Alright, no, it's pointing to the x-axis. We want it... I'll just make it put it pointing to the z-axis. Yeah, that sounds good. Because we're gonna have to send this to the 3D printer later, and I don't really want to mess with orientations. Yeah, this looks good. Anyway, so I mean it is pretty flat, so we're gonna basically it will be sitting right on top. But anyway, enough of that. I guess we can finally start with some design. Right, so we're gonna want to first make a lip, so it basically holds itself. Oh, hold on. No, wrong diameter. Wrong. Yeah, we're gonna want to make a little lip here, to make sure it doesn't like just slip off. Actually, we're gonna be making a lip both on the inside and on the outside, so it will be a source of friction, but hopefully less than just having two pieces of plastic rubbing on each other. I actually gotta see later what are the tolerances on the 3D printer, so Yeah, we'll see about that. But anyhow, mm, right, should be good. We have barely any room left. Reminder that this could be later gonna be just sitting on top, so can delete this in the middle. I will want to fill this edge though. Pull it up a little bit. Hold on, what is it doing? Oh no, wait, I don't want to pull the edge. I want to pull this face. Yeah, let's make a roll 2 millimeters, since I'm pretty sure it's gonna be around that much, the tolerances. I also want to pull this one, so it fits snugly on top. Look at that. Looking pretty great if I say so myself. Though I'm the designer, so I'm kind of biased. I also don't have the slip ring yet, so I'm just gonna leave a generic hole here. Just so it can be fitted later on. Looks a little bit off center actually. Is it? Nah. Might be just, I don't know, it just gives me the vibe. Anyway, yeah, back on this plane. Hold on, this is supposed to be 85 millimeters, so I want to make this 83. Ah, shit. Why is it showing my keyboard? What was it showing my keyboard? Right, refrain from using the number pad. I forgot I had macros in there. Silly mistake. We're gonna make, what? About 20 millimeters of wall? That's what, 2 centimeters? I don't remember how much I did of wall last time, but yeah, we'll see. Because anyway, I did already do a preliminary also sketch of the. I want to make another unused object. New solid. Yeah, let's make this 28 millimeter by 28 millimeter. Just. Yeah, it should. Seems a little bit too much actually. It's 1.6 millimeters. The thickness of your standard PCB. So we're gonna use that as a guide. Move this. Move this inside. Hold on. No, I don't want to move the face. I want to move the entire object. Move this inside. We can cut off that the little bit later. This actually might be a little bit too small. Also, I need to move it up. There we go, now it shows up. I think I can... No, hold on, isn't it? I want split body. Yeah. Hold on, what is this? Which solid is this? Here. Alright. Yeah. Alright, it should be good. I mean, at least it's not showing anything out. I should probably shrink this too. No. Wrong. Right. So solid, I want to... I'll just move it a little bit back now since we are already... Yeah, alright. So looking from above, it's gonna be looking like a little bit something like this. Actually, I could probably pull this a little bit more, so it covers the exact center. Yeah. And right, so this is just a placeholder PCB. I will have the actual one filled in later. But yeah, now we can actually import the hold on, I want to put it in the SRS dock. Is this? No. Now I want to import the RxTX modules to have an idea of the size. And yeah, of course, I already pretty much made a mock-up of the entire PCB, just to speed things up a notch. It's actually looking pretty big for this. Though on my... Though on my other testing, it fit pretty well. Well, we'll see about that. I want it just right. All right, looks good. Gonna be a little bit top heavy, if I'm gonna be honest. Measure. No, I wanted to measure the angle. I want to measure the angle, but I'm not actually sure how. It's looking a little bit more cramped than in my initial, probably because I did the entire thing in like, what was it, 80 centimeters? Yeah, I think so. Is there really no way to make an angle, to measure an angle? Maybe I'll just have to... Oh, hold on. Yeah, around 18 degrees should be fine. No, I just gotta extend this up to here. Oh yeah, we're gonna need some more space. Or either that or just put the one on top of each other. But that would decrease reliability. We might have to run it slower then. Instead of to increase the angle. No, faster. Shit. Yeah, no, run it faster to increase the angle. Or alternatively use an receiver and transmitter setup, which would also be pretty interesting, but I have my doubts about the cost. No, I mean, if we really want to keep costs down, I'll just use one of those off-the-shelf ones. I even concern myself with this, but yeah, no. We'll see. We will see what we can do. If we do 36 degrees, we're gonna end up a little bit. Yeah. Here. How does that look? A little bit better, if I'm gonna be honest. Because now I can just copy paste this, move it around. There, that should be 36. 360 minus 36. It's gonna be 324. And now we're gonna be having some interference. Ooh. Yeah, I did not account for that. Not much, so we could probably reduce the PCB area. Hold on, I need the top-down view. The perfect top-down. Yeah, we might get away with it just reducing the PCB area. No, this isn't even centered. If we were to center it though, how much will we have to cut down? A lot. We have to cut down quite a big chunk though. Oh, it's still doable though. Still doable. Yo, what are you? Oh, because I'm decreasing on both. Oh. No, but then the connectors get tangled up. So increase even more the angle. Make it 3 RPM. Well, 3 revolutions per second. Because then we got a 54 degree. How will that look? Oh, hold on. No. So, yeah, it's just gonna be 18 36. Oh, okay, 54. All right. Another piece of the pie sliced. Yeah, if we do 54, I'm pretty sure we can manage. So you'll have to do 3 revolutions per second. All this is going to be adjusted with the gearbox later, so it's not really that much of a big deal. So I want to move this, just everything. .306 degrees. I should probably move a little bit further to... There we go. And we're gonna have to increase the PCB a tad, this one. There, but that should be just enough for this, for now, at least. So yeah, I think this works, so I can finish with this is gonna be all encapsulated. And we're gonna have a lid later, but that can wait. Because now we gotta take a look at the bill of materials, really. So looking around, I was looking around a bit for. I did find this project, which is pretty much already pre-made. It's basically microcontroller send signal. Well, part of the piece, part of being an engineer is pretty much just understanding what's going on here. But anyways, yeah. So microcontroller sends the signal to the emitter here. What happens next is it's gonna receive it, and it gets amplified. This is a filter. It gets amplified, filtered, probably to make sure that it doesn't get deleted. In case if you filter first, it might pretty much just reduce the signal to noise. So yeah, preliminary amplifier filter at what was it? 40 megahertz? No, not megahertz. 40 kilohertz. Another amplifier. And then, well, a hysteresis comparator. So pretty much, here's the reference. Here's the it's just pretty much it's just use a comparator. Here's the reference voltage. Here's the output. If the output goes above the reference voltage, it turns this on. It turns this transistor on, and the signal gets sent. Because while this is turned off, there's pretty much no current, there's no voltage here, so it's just well, there's no. Oh, okay, no, this is a pull down transistor. So yeah, there's basically going to be 5 volts eternally here when this is on. Because this is on, this pulls everything down to 0 volts. Yeah. Yeah, the problem is the hysteresis design doesn't really. I think it doesn't really do too well for a rotating element. I will do a prototype on this one. I just need to get the parts. I think the guy this email from. I'll give a shout. I'll put a link to this and I'm already giving him a shout out. This is from 2014 too, so it's pretty. Yeah, I have no idea what's this, where this is from, but I will put the link in the description below to emails, projects, and reviews. It's he gets the base this tiny ecolocator from AliExpress. It's really simple. It's really cheap. And this is basically the secret he does. He pretty much makes it better. Optimizes the filter and changes the microcontroller to an ATtiny24. He doesn't put his program here though, does he? I feel not. I feel like not. So. Well, we're gonna get to that later. So, yeah, I will see if I can work on one of these designs. So the bill of I will make a bill of materials though. BC847. I will take a look at these components. The LM324. I'm not gonna use the LM324. I'm gonna use the OPA4342. just for tests. So let me make a little bit of materials here with Notepad. So for this, we're gonna need two piezo cans, one for transmission, one for receiver. I realize Notepad isn't the best place to do this, but you know, I'm a boomer in spirit, so I am gonna use the plain Arduino for the. I'm gonna use the plain Arduino to just do prototyping, and then when I'm ready, I'll do the actual. I'm gonna make an actual board for it. Oh, I mean, we could just already start designing the board to maybe get it already fit in properly and do some prototypes. But yeah, a bunch of resistors and capacitors. I will have to write them down probably individually. Well, I will see if well, the main components are pretty much I said on OPA 342, which is basically the OPA 342 except with 4 op amps in the package. I am not entirely sure if the BC847 is necessary or if it's just. Let me check the datasheet real quick. BC847 by Nexperia. All right. Well, it's a small package, so for surface mount. That's probably why it's used. Honestly. Doesn't give me any indication on which model it is though, because there's the group A, group B, and group C. But I'm going with the assumption that it doesn't really matter, since it just really needs to act as a switch. At least I think in this case it just acts as a switch, because when this is pretty much a comparator. When it gets turned on, it's just gonna pull this down, and no, because this is isolated from this pretty much, so it's gonna pull this down, and it's just gonna pull this down and make this go to 0. And I don't see anything really particular about this, so probably any BJT or MOSFET could work for, at least for prototyping purposes. Since I'm not gonna be using the cans that the AliExpress special cans, I will have to buy the slip rings from AliExpress though, unfortunately. But yeah, just for. Do they have these in? No, this is just the pack. These are the 2 types of packages, aren't they? Yeah, not really particularly good for prototyping. So I will have to find an equivalent one for that can go on the breadboard. But yeah, pretty much. Let's go back to this. Yeah, other than that, it's just pretty much resistors and capacitors, of which the values I will count later and just post below. But, well, the other idea was, let me open up Design Spark PCB real quick. Hold on a second. Yeah, I'm gonna have to log in again. Give me a second. This is the first time I use this in this account. Where is it? All right, there we go. File, new project. New project name, and let me go to my phone. So this is going to be the main detector board. All right. Schematic designs. I want to open a new schematic. No, I want to open a new schematic. Main board. Huh. I'm probably gonna have to put it on the folder later. Anyhow, so the idea is, which components do I get here? It's the first time I actually use the design spark, so design spark. Find. Yeah, I don't think I'm gonna find it like this. Are there online libraries? Seems like I've come pretty unprepared for this. Yeah, I was expecting it to. Anyway, yeah, I'm just gonna have to sort of wing it. Anyway, so we're gonna have to OPA 4342. Yeah, no, hold on a second. That's not an OPA 4342. No, there are no OPA 4342s. What do we have here for MOSFETs? We don't have anything for not the MOSFETs. Yo. They really don't have any op amps here. Alright, let's see the LT Spice library. LT Spice for the rescue. Yeah, op amp. Alright. The 6 terminal. No, 6 terminal. Op amp here. The simple one. So yeah, I guess we're just gonna yeah, there's gonna be a 3 op amp design. Not really much. So I will end up wasting one. I will inevitably end up wasting one. So not much that can be done. But yeah, I will follow the components, the passives at least, that the guy puts out. So since no point in doing it again if it's already there. So RCR. Maybe I could have used Gitgud for this. You know what, the components aren't here anyway, let's just switch to Gitgud. File, new, project. Right, so back to the schematic. Place symbol, oh, it's Shift A. Loading library, loading library, loading library. Speaker ultrasonic. Alright, yeah, this works. Well, this is gonna be the receiver, so do I have the 4342? 4340, close enough. A unit A. Unit B and unit C. Unit D, I don't want unit D, and I'll get unit E just to get everything. Just get everything. R. So resistor here. Resistor here. Where else is the resistor? I'll place all resistors first. One here, one here. One here. On unit. So basically, this is the first amplifier. This is going to be this is the filter. Another one here and another one here, and then another amplifier. Yeah, this is a little bit sloppy, but I can always come back and how do I rotate it again? Ah, shit. Mirror, Y, X. Well, let's start moving from working from the back again. Then C. So we're gonna have a resistor and a capacitor here. Start drawing traces. Right, now here we're gonna have to have the same secret sauce that we used on the last project, which I wanted to kill myself for, because it was just It was just a pain in the arse. He also had some capacitors in for filtering, so I guess I'll do that too. I mean, it doesn't really hurt to be VCC and ground. And back to wiring. Yeah, pretty much what he does here is what I did last time, which was just make a voltage divider. Instead of using an op amp to basically smooth out the waveform, though, he just goes berserk and on all three of them, since they're all gonna need to be biased, have some common mode biasing. And well, this all gets grounded. Right, up next. Okay, so next one is gonna be a little bit complicated actually. Let me move everything a little bit. Right, so up next, what we have? These two make a divider here. Start off. It's not really a divider, but well, it is a divider, but connecting to the half rail. Then we're gonna have 3 capacitors, 1, 2, 3. Because it's a second order filter. There we go. Then move this a little bit more. Forward. Another cap here. I will put in all the values later too. But for now, just enjoy the disorder, I guess. But opposed to what he was doing, oh, hold on, I need to connect this part too. But opposed to what he was doing, the plan here is to basically, let me get an 80 meg 328. They have 80 tinies actually. Yeah, they have 80 tinies. Not sure which ones they do. Yeah, the 2 and 2, which is the one I'm actually planning on using. Right, so got a VCC and a ground. I'm gonna have to get the AT Tiny 2 and 2 data sheets real quick to get the pin out. Here it is. Pin out. Right. So I'm gonna do I2C on this one. So I wanted to leave PA1 and PA2 free. Then, well, I want to leave PA0 free because that's the reset and new PDI. I mean, I could probably use it, and it does use that for SPI, but I guess because it's also the select. So, well, I guess PA0, PA1, and PA2 are reserved, which leaves us with, well, PA3, PA6, and PA7 to work with. So I'm feeling we're gonna put this on PA7 just to get it out of the way. And basically just like this. And yeah, this is gonna be just a plain old analog signal. It's just gonna be a plain old analog signal, and then I'll do some processing, some signal processing magic to actually get to the position. I'm not sure how exactly. I'll leave that to the testing later, but yeah, no. So these ones, I'll just put them down here as reserved. Then I believe there was the, oh yeah, this used two lanes for transmitting, didn't it? Yeah, 2 lanes, so T1 in and T2 in, which would give out T1 out and T2 out, which means it's gonna be a pretty busy board, I believe. Max 232. Yeah, here it is. Yeah, this is gonna be a busy little board. We just plug in directly. So PA3 and PA6 just plug in directly at T1 in and T2 in. There we go. Then there's another piezo. There's another piezo transducer here. That's T1 out and T2 out. Then VDD, ground, and all that good stuff. Let me get it in here right now. Which in this case is VCC, just because. And yeah, I can do some signal processing on the chip itself, and then just some preliminaries, just to not send a bunch of garbage data to the main well, sonar processing unit. Then if I recall correctly, this needed a few capacitors around. Yeah. One here, one here. Did VS Plus and VS Minus have a capacitor too? I wonder. Let me check. I'll just check his, since it's pretty much an identical copy of the... Right, so V Plus, okay, it has a capacitor with the top rail, and V Minus has one of the bottom rail. So I may actually have run out of pins. If you can believe that. Is the 2 and 2 smaller than the 80 Tiny 24? I wonder. Because this one is a 14. Oh, it's a 14 pin. This is an 8 pin. Right. That's probably why. Yes, you know, if you don't have the right tool for the job, why even try? So yeah, let me get the AT-Tiny24 datasheet real quick. And I guess we'll change that. There we go, that's a lot more ports. Yeah, I think I underestimated how many I actually needed. Anyhow, AT-Tiny24, here we go. I want the... Oh, this doesn't have a multiplexer. This doesn't have a port multiplexer. Alright, so we just gotta take it at face value, what each part is. So... we have a few ADCs. I wanted to see where is SDA and SCL. Alright, SCL. And SDA, so 7 and 9. I really do want to leave another pin open for maybe an interrupt. Which pins were they again? Right, so 7 is SDA. I'll just put 7, 8, 9 then. Why was pin 6 scared of pin 7? Oh god, I'm not gonna do that, am I? Does pin 7, pin... No, hold on a second. This is wrong. Did I get the wrong... Oh. Oh. I know what, let's just wire this for QFN. I'm not really a big fan of SOIC anyway. Yeah, but I already have it out anyway, so... Right, so the only problem is SCL. Dude, what the hell is it? Yeah, do not connect. Oh, alright, so it's pin 1 and pin 16. And I guess I'll also leave pin 20. This is a little bit messy. And so hold on, pin 1. Yeah, from pin 1 then to pin 16 and 20. Wow. Anyway, so then I will have to leave one ADC. I'll have to leave one ADC also already reserved, so yeah, pin 2 I guess is fine. It's ADC 3. Then Xtal. What was Xtal again? Didn't this have an internal oscillator? Or is this... I would actually prefer to use the internal oscillator since that saves space on the board. Programmable with separate on-chip oscillator. Alright. Yeah, so this does have an oscillator. How many megahertz is it, though? I am a bit quiet now, but it's because I'm thinking. I'm looking for stuff here. So, right, here we go. ADC clock. Oh no, hold on. So I need to provide an external clock. Oh damn. Yeah, so I'm gonna have to put an oscillator, a clock. Kind of a shame, really. I would much rather do without one. Just have a. Oh, hold on. Oh, there's an 8 megahertz oscillator. Oh no, okay. Yeah, so we'll probably have to use an external clock unless I get another chip. So yeah, just keep in mind XTAL1 and XTAL2 are off limits, so it's gonna be PA1 and PA2 for this. And PB2 is going to be the. Hold on, if I recall correctly, did he? Oh, this is connected straight to VCC. Ooh. All right. So basically, this is gonna be powering the chip and just turn off high voltage. Yeah. Makes sense, I guess. X. Yeah. So this is gonna be plugged in directly here. There's gonna be a 1K resistor here. A few caps. Right, one. Where were they? So one just here, and the other one. Oh, hold on, I'm supposed to cap this one too. And yeah, I didn't forget about these, I'm just ignoring them. This is getting a bit messy with all these wires. But yeah. This should be appropriate. Yeah, I'm pretty sure this is gonna be the. I'm pretty sure this is what it's gonna end up being. But we'll see. At least in terms of the circuit, it should be. I need to find the values for the final I just need to find the values for the final amplifier, since that's what's really gonna make my magic sauce signal processing work, if it does work. Or else we're gonna have to change a little bit the paradigm. But I guess for now it should be okay with this. I mean, what is there else to do here? Not much. Just name everything and put the values. Oh yeah, there's already SDA, STL, and interrupt. Just putting the finishing touches on a connector. 0103. This one was. I guess I'll just make it. I'll just make it male. There we go. So in actuality, there's also going to be a connector here. I'll actually have to put them in different schematics, I think, to make them fit properly. I don't know. But yeah, it's a little bit of messy. A little bit of spaghetti here. No, nothing too major. This is not gonna be tested just yet. So yeah, I guess that's it for today then. Oh, that's all we can do today anyway. Cause I actually, before we go, let me see this. I wanted to make, how do I make a wheel? A cog wheel. Can I make one just, ooh. Can I make a cogwheel just with Thank you, Windows Defender. Okay, so I'm just gonna have to create pattern. Yeah, so I'd probably have to think about the gear before I do this. Though I'm pretty sure I'm gonna make it a 5mm bit. No, 5mm is a bit too much actually. Huh? Wait, what did... I feel like 5mm is going to be too much. isn't what I'm thinking it is it? Nope. This isn't what I'm thinking it is. Okay, no, I want to keep those two. Right. So hold on, maybe I need to project these. No. Yeah, why isn't it projecting then? I can't make this curve a part of the solid, can I? Nope. Maybe if I... Yeah, doesn't seem like it's gonna be working today. I need to box it in, maybe. No, this isn't gonna work. All right. No, hold on. Yeah, all right. So let me follow this. So first I draw 2 lines. Then I need to project them onto the surface. Where's the other line? Here it is. Doesn't want it to project apparently. Oh no, wait. Really? Oh boy. Yeah, I'm taking a beating here. Let's try somewhere else. Maybe it's a problem with that corner. Or maybe, just maybe, I could. Yeah, that might work. Right, oh. So, curve 1. Select, project. Yeah. I think we want to pick. Yeah, that's acting a bit weird. Yeah, I'm not gonna lie, this is acting up a bit. Oh, hold on. Oh god. What is going on? No, I can't pick the Y direction. What the hell? Holy man. Oh boy. Oh boy. Yeah, no, it doesn't work. Because now this is divided it in two. Oh, it's already divided in two, apparently. Alright, yeah, now we're back. Holy. Yeah, I'm taking a beating here. That doesn't work. Now move. What was it again? Oh shit. Oh shit, it was muted. Yeah, I think this should be okay for then. Sorry if you came in and I wasn't talking. But so yeah, we already got the schematic going. I gotta sort out the. I will buy all my other stuff to sort out the what processing magic I'll do. We also got the CAD model started on the CAD model, to be honest. So let me save it. Yeah, so I already got started on the CAD model too. There should be. I mean, it should be. Should be fine. Oh, I might have to find a way to detach the lid, the bottom, actually, now that I think about it. But that will come with time. So yeah, I guess, thanks for watching. If you liked, leave a like. If you want to see more of this, don't forget to subscribe. And I guess we'll see you next time.